I got salmon from Kroger. It was like
Okay, all right. Somehow we have to jiggle it in order to get it to work. All right, let's see. Turn it this way. Good. And excellent. We have the notes here. Okay, so let's glasses. That's better. Okay, let's see. Oops. Okay. 6. That's more helps. Hmm. Okay. Is that- okay. So did anyone try accessing the videos at all yet on Kaltura? No, yes. Are you guys interested in accessing the videos on Kaltura at all? I'll keep trying to post there. I'm just wondering if they're available. They're only available on Zoom for 30 days. So I'm trying to get a place that the video for the class will be actually available to us. Yeah. How many people do we have out there? We have 4 people so far. Okay, can you hear me, Zoom people? Six now. Everybody okay with this? You guys are all okay. Let's do a little sound check. All right, for people who are watching virtually, can they hear me?
Yes.
Yes.
Yes?
Yes, sir.
Can someone say something?
Hello?
No, I mean,
I don't know.
Let me see if I can get. Oh. No, it should be up all the way. Can someone say something who's watching virtually, please?
Yeah, it works. Hello, hello.
Hello?
Testing,
Let's
testing.
see. Hoping that we can,
Am I
I
muted?
don't hear anybody. This may not be a good time. I have 16 participants. One more time. Hello out there. Can you
Hello?
hear me?
Yeah, we can hear you.
What's going on with the sound here? Let's see here. Okay, so I can see myself. Then let me see
Testing,
what's in it.
testing.
Is there anything in the chat here? Let's see.
Hello?
I don't seem to have any sound here. That's the problem.
Yes.
Hello.
See if the volume needs to go up here.
Testing, testing.
Can someone say something?
Hello? Hello?
One more time.
Hello? Hello?
Oh, good. Okay, we're getting sound now. Thank you. Okay, one more time.
Hello? Hello?
Hello?
Okay, great. Okay, I think we have sound. Thank you. All right, now I see how we have to do this. Okay, so it's not here. It's on the dash. All right. So the first thing I'd like to ask is, did everyone receive the email that I sent out yesterday about the homework? Yes. Good. Okay. So what I'll do is once the grader has set up your folders on Microsoft OneNote, I will send out a message to you alerting you to this. Okay. And so hopefully, it'll go smoothly on Wednesday. And I mean, we have some grace time too. It's not like there's a hard deadline to turn in the homework. So, we'll try to get it to run smoothly the first week. And then hopefully after that point, it'll be pretty smooth turning in your homework. Okay. Good. Okay, so let's start by reviewing a little bit. So last time we were looking at a method to solve systems of equations. So we're looking at systems of equations. And for short, I'm going to write this as AX equals B. Now, I haven't really explained this yet, but this will be just my shorthand notation, so you can actually get used to this later on. So next week, we'll actually explain what AX equals B means. It's just a shorthand notation for writing out a system of equations. So the system of equations could be a system involving m equations and let's say n unknowns. And we've seen plenty of examples of these. And last time what I did was I showed you how to solve systems of equations using the method of Gaussian elimination. So we had this method called Gaussian elimination. Another term that's used is row reduction. Okay. So what you do is you have your system of equations. Let me call it AX equals B. And you put the A part over here. Those are the coefficients. And then the B part is over here. Okay, so we'll do lots of examples today. And the idea with Gaussian elimination is to transform this matrix into something which is of upper triangular form or row reduced form. So the idea is to row reduce so that it looks something like this with zeros underneath and something else over here. Okay, so we do steps to actually make it sort of upper triangular, And then in order to solve the system of equations, we do back substitution. So then apply the notion of back substitution. Okay, any questions on this?
I have a quick question.
Sure, go ahead.
So in the textbook, they were talking about like pivots, like row pivots and column pivots. Will you be touching over this?
Oh, yes, I will. I'll do some examples where we actually talk about the pivots.
Okay,
Yeah,
appreciate it. Thank you.
I had another question about the textbook as well. There was a couple of examples where for the values that we're solving for or the solution set, I think they were just arbitrary variables
Yeah.
or asking for us to solve for them. I don't think we've done an example like that as well.
Right, so the thing is, the principle is the same. I mean, so what you have to do is you just have to sort of, once you row reduce, then you actually, solve for those variables by back substituting. I think I have an example on Friday that I'm going to do with that. Okay?
Okay, thank
Okay.
you.
Good. Other questions? All right, so let's continue on here. So let's start with some examples. All right, so here are my equations. So here's x plus 2y plus z equals 0, and 2x plus 4y plus 2z is also equal to 0 too. Okay, so it's two equations, and how many unknowns? How many? Three.
Three.
Okay, so here's a system of equations. We sort of load it into the matrix. So let's do that. So I sort of draw my line here. 1, 2, 1, 0, 2, 4, 2, 0. Okay, everyone okay with that? And now what we want to do is we want to row reduce. So the idea is the first thing we're going to do is we're going to look at this part. This is going to be the pivot here. So the pivots are sort of the non-zero entries where you're going to use to knock out things below it and make them zeros. Okay. All right, so who can tell me what we should do first? Go ahead. Yes, and then add it to the very good. Okay, good. So that's what we're going to do. So minus 2, I'll even write it down here. Minus 2 times row 1 plus row 2, and insert the new thing into the new row 2. And maybe that's a cleaner way to say it. Okay. All right, so let's do that. 1, 2, 1, 0, 0, 0. What's next? 0. 0. What's next? 0. Okay. Okay, who can say something about what the solutions are going to look like at this point? There'll be infinitely many, right? So this equation up here, or this system, reduces down to just looking at x plus 2y plus z equals 0. All right, now how do we sort of solve this algebraically? So the first thing is, let's identify the pivots. So remember, this was a pivot over here, okay? So the free variables will occur in the columns that are not the pivots. Okay, so let me write that down. So the free variables correspond to the columns which are not pivots, which do not have pivots. Okay? So in this case, it's a second and third column, right? And so that means that so this one corresponds to the X, this one corresponds to the Y, and this one corresponds to the Z down here. So the variables that we have to make free are which variables? Okay, Y and Z. So Y and Z will be the free variables. Okay. So why don't we just call them something? Let's say Y is S and Z is T. Okay, so once you set things to be the free variables, then what do we do next to solve the system? Go ahead. Yeah, we just plug it in and we back substitute. Okay, so now I'll do back substitution. Okay, move that up. All right, so what do we get? We get X plus 2Y plus Z equals 0. Okay, so now I want to just plug in the free variables. So this is 2S plus 2T is 0. So we know what X is now. So that means that X equals minus 2S minus 2T. Okay, so we know that Y is equal to S and Z is equal to T. And now what we can do is we can express the vector X, Y, Z, right? So the solution, so all this is very clean.
Professor,
Yeah, go ahead.
where did the 2t come from? Be 1t?
Oh, sorry, I apologize. So there is no 2T there. Okay, thank you. I'm glad that people are very attentive. Okay, so let's see, which one do we have to erase? This one right there. Okay? Everything good? Okay, now I have to do a little bit more erasing. Let's see, minus 2S. How about that? Everything good? Take a look. Sorry, I don't have one of those fancy, I don't have one of those fancy, pencils that I could just turn around and erase. I have to I have one of those cheap ones. So, all right. Okay. All right. So now, now that we have this fixed, let's write the solution down. So this is X, Y, Z equals X is minus 2S minus T. Y is S, Z is T. And now we can just separate out the S and the T, right? So S is going to be, well, the ones with the S is minus 2, 1. What's the next term? 0, good. And now let's separate the T out. And so what vector do we get down here? Very good. Okay, and this is where S and T can be any real number. Okay, so we actually solved the system of equations. What does the solution set look like? Oh, what does the set of solutions look like? Is it like a line? Is it a plane? Is it like grease? What is it? Well, think of it this way. You have one vector going this way and another vector like going this way, right? And you just look at all sort of combinations of those vectors. So what are you going to form? Plane. And does that make sense? Because we're looking at the solution of, we're trying to look at everything which is a solution of, let me see, where did it go? Oops, that's not what I want to do. Of X plus 2Y plus Z equals 0. And that's the equation of a plane. Right? And so what I've done is I've actually described the solution sort of in a slightly different way by solving the systems of equations. Okay.
I have a question.
Yeah, go ahead.
At the top of the problem when we started, why did we multiply by -2?
Because what I want to do is I want to match the pivot, a multiple of the pivot, to what's below the pivot so I can knock it out and put a 0 down there.
Oh, okay. Thank you.
Okay? Good. Other questions? We'll do more examples in a second. All right, let's do another example. So I really want you to get the feel for this. So we're going to do examples so that, you know, you sort of get practice at thinking about solving systems of equations. We'll be getting very, it's sort of the bread and butter of the course. Okay, let's do another example. The more examples you see, the more experience you get, as you can expect. Okay, so I have x plus 2y plus z equals 0. Okay, so this is an equation of a plane. And then I have 2x plus 4y plus 2z is equal to 10. Okay. I want to know the solutions for this. What do you think they are? Sorry, there are no solutions. Okay. So great. These are planes which are parallel to one another, right? I mean, so now I want to actually use the Gaussian elimination technique, and we want to be able to see that there are no solutions. Okay. So there should be no solutions. All right, so now we're going to just set it up in terms of Gaussian elimination. 1, 2, 1, 0 here. And 2, 4, 2, and a 10. Okay, so again, we do the same procedure, right? We locate the pivot first up here. And then what do? We multiply the first row times -2, add it to the second row, replace the second row. Okay? Same as what we did in the last problem. Okay, so let's do that. So 1, 2, 1, 0. And what do we get for the bottom row? Good. All right, does anyone see a problem here?
You can't have 0 equal to 10.
Right. So what does the last equation say? It says that 0x plus 0y plus 0z is 10, right? So like you said, 0 is equal to 10. So this cannot happen, therefore there's no solution. Okay, so we know that 0 is not equal to 10, so there is no solution. All right, so what this shows you is that the Gaussian elimination technique can also tell you when there's no solution to a system of equations. So when you start running into things where you have zeros someplace and then you have non-zero things like in the columns, then you can tell that the system has no solution, does not have a solution. Okay. All right. So let me just make a definition. I think this is in your book. System of equations, we'll call it AX equals B, is consistent if there is a solution, and it's inconsistent if there's no solution. Okay, so in this example, the first example we did, this is consistent. There are infinitely many solutions, so there's at least one. And then in this example, number 2, is it consistent or inconsistent? Inconsistent. Okay, any questions on this so far?
I have a quick question about notation.
Yes,
So in the textbook, you know how you draw a line where the equals is supposed to be in the matrix?
yes.
Well, in the textbook, there's no line. However, when
I
you write
would-
it, there's a line. Does it matter or?
Well, let me say it this way. I think in your homework, I would suggest putting a line there. Then it's kind of, then you sort of know where the equal signs are. The book, I've used the book before, and it's sort of bad form not to have the line in. Okay.
Okay, so
I
just
would
use the
def-
line?
Yeah, so I would use the line then. Because sometimes we're not going to use the line for other reasons. Okay, but when you solve a system of equations, you should try to say what the A part is and what the B part is.
Thank you.
That's a good question. Okay, other questions? All right. Great, so we'll just kind
Actually, I
of,
have one quick question.
sure.
I'm
go ahead.
not sure if we're going to get to this on Friday, but I noticed in the textbook on 1.2 or section 1.2, they were doing a couple problems in reduced echelon form.
Yeah.
So have we just not gotten that far yet, or?
Well, it sort of depends on whether, I mean, I'm trying to hit sort of the sort of basic way of actually doing things. You may have to adjust it just a little bit to do it in reduced echelon form. But for the purposes of this class, you're not going to really need to know so much the differences.
Okay, thank you.
Okay. Yeah. All right. All right, I want to do one more problem. And then we'll start talking about something else. Okay, so this is a problem just to kind of, it's sort of executive summary problem. So it's good to sort of test our knowledge and make sure that we've understood what has happened. All right. So let me start with this. Could do anything for this? Oh, I guess not. Okay. So suppose we have the following matrix here. Okay, so 1, -2, -1, 3, 0. Okay, let's say I have a 0, 0, 0, 0, 0 here. And I have a 0, 0, 3, 1, 0. Okay, so this is, I have a system of equations and I've actually have it in this matrix form over here. Okay, can anyone suggest how to solve this system?
Swap rows 2 and 3.
Okay, so we want to switch rows 2 and 3 and see what happens. Okay, so it's a good idea. So now we start making it look like this row echelon form. Okay, so 0, 0, 3, 1, and a 0 here. And then 0, 0, 0, 0, 0. Okay, good. All right. Now, let's see, how are we going to analyze this? What should we think about next? I'll let you think about it just for a second. Do we need to reduce it anymore? Okay, we don't need to reduce it anymore. So we need to actually figure out where the pivots are. Right? So the way actually, if it's already, this is already row reduced. Okay. And so now what we should do is we should kind of look along the rows and find the first non-zero entry. Okay, so I want to look along this row here. Okay, so where is the first non-zero entry? Which one is it? The 1. Okay, so this will be a pivot. Okay. And then we look along second row. Where is the first non-zero entry? Where is it?
The 3.
3, good. Okay, and in the third row, there is no non-zero entry. All right. So this is a way, once it's in the row reduced form, this is how you locate the pivots. Okay. So what we did was here, we located the pivots. All right. Okay, so let's call these variables something. Let's call them X, Y, W, and Z, for example. Okay. Which variables are the free variables? Y and Z. Right. So W and Z are the free variables. Sorry, Y and what? Oh, does that look like something that, that's actually a Z.
And the first one, the W, is W not a free variable? Because it's in the same column as this.
Oh, sorry, I'm sorry. Y and Z. Thank you. Okay, good. Okay, Y and Z are the free variables. All right, so let's set them equal to something. So let's say Y is equal to S again, and Z is equal to T. And then what we'll do is we'll just back substitute back up. Okay. All right, so let's do that. So we start with the equation involving 3 and 1, right? So let's write those equations out. So that's 3W plus Z is equal to 0. Okay, so Z is free. So 3W plus T is 0. And what do we have now? We have T is equal to minus 3W. Sorry, 3W. I want to do it the other way around. Sorry about that. They really penalize you for erasing it there. Because let me erase here. Okay. Let's go back. All right, so what I want to do is I want to solve for W. Okay, so that's what I want to do. So that means that, whoops, 3W is going to be equal to minus T, and W is equal to minus T over 3. Okay. All right, and then what should we do next? Yeah, go ahead.
Substitute the W and the T back into the very first one to find X.
That's right. That's exactly right. So now I have X minus 2Y minus W plus 3Z is equal to 0. Okay. All right, so X minus 2S plus T over 3 plus 3T is 0. Okay. So what do I get? I get X minus 2S. Right, so how many T's do I have here? 10/3. Thank you. 0. So X is equal to 2S minus 10 over 3T. And we'll now ready to write the solution out. So we need X, Y, W, and Z. I want to get them in the right order. Okay, so what do we have? We have, let's see, 2s minus 10/3 t. Okay, what's y? Y is s. W is minus 10/3, t over 3. And z is equal to t. Okay, so let's just separate out the s and the t. Later on, you'll see why we're going to do that. So this is a, so what's the vector corresponding with the s? Anyone?
Negative
2100, right? Is that right? Okay. And then the vector corresponding to the t will be what? Anyone?
negative 10, 30, 0.
It'd be negative 10, 3,
Okay, good. 0. Next one.
negative 1/3,
Good.
and 1.
Good. And then s and t are real numbers. Okay, so that's what the solution is. Okay, any questions on this? All right, good. So I think we've had enough Gaussian elimination for the day. So let me move on to talk a little bit more about vectors next. Okay, so we're going to start kind of a new subject, and then we'll come back to this. All right. So I want to talk about vector equations. All right, so I'm going to do this a little bit more general than what I've done in the past. So instead of 2 variables, I'm going to work with n variables. So let me just recall a vector first. Well, there are two things that you have to think about with a vector. You have to think about direction and also how long it is, the magnitude. Okay, so when you specify direction and you specify the magnitude, you get a vector. And that's usually represented by some sort of arrow like that. Right? Now, if I look at vectors in Rn, so n-dimensional space. So this is called Rn. Okay. So Rn you could sort of think of as being just points. x1, x2, let's say x of n, where each coordinate is actually a real number. Okay, so for example, if you take R2, you just get the 2-dimensional plane. And vectors here can be represented as points, x and y. And the vector can be represented as an arrow point from the origin out to the point x, y. All right, so what we'll do is the convention will be to consider vectors as columns. So the convention will be the following. We're going to think of the vector as being a column x1, x2, up to xn. And this is going to be inside of Rn. So the coordinate then gets sort of transformed into this column. All right, so again, there are two operations. There's vector addition. And so if I take two vectors, which I'm thinking of as columns, x1, x2, up to x sub n, and I add it to another vector, y1, y2, up to y sub n, then what should I do when I add vectors? Good. Okay, so you just add the components. Okay, so that's how you do vector addition. And then you have another operation called scalar multiplication. And the way you think about that is you take a lambda times x1, x2, up to xn, and you just multiply in. Okay, so lambda is some real number. Okay. All right. Now, the next thing I need to talk about are linear combinations. Okay. So let me start off by sort of a basic example. So I'm going to take a vector which is the linear combination of two vectors. So if I take V and let's say it's C1 times the vector V1 plus C2 times the vector V2. Okay. So let's think about what this looks like. Oops. No, don't want to do that. Keep on going. Okay, let's see. All right, so let's just think about what this looks like. So let's kind of draw the vectors in three-dimensional space. Okay, so pictorially, I have a vector like this. Let's say it's V1 down here. Okay. And so what am I going to do to V1? I'm going to sort of stretch it, right? So do I dare try this? Okay, let's try something a little bit new today. All right. All right. So let's see. If I do that, and let's see. Suppose I make a red here. Okay. So let's see if this works. All right. So now I want to stretch it. So I'm going to use this and call this C1 V1. Okay. All right. So I'm just stretching it out. Okay. So let's go back to the black. And I have another vector here. Let's say it goes this way. And this is V2 over here. And then I'm going to stretch it. I could stretch it also in the other direction, but let's just pretend we're stretching it in the positive direction. And I'm actually going to stretch it by doing this over here. This is C2 V2. Okay? So then when I take the sum of those two, so let me just write this out. This was right on the block. So if I take the sum of the two, I just have to move this one over here, right? And then when I take the sum, the linear combination will be this vector here, C1 V1 plus C2 V2. Okay, does everyone see how we kind of did this? Okay, so when I put constant times the vector, I'm sort of stretching things out, and then I sort of have to add the vectors by sort of putting the tail to the head of the other one. All right. Okay, so this gives you sort of motivation for trying to define linear combinations more generally. So let me give you the general definition of a linear combination, and then we'll study this. So let's make this following definition. So let V1, V2, up to V sub t be vectors in Rn. So they're n tuples. Okay. So the vector y is a linear combination of these vectors. If y is equal to C1 V1 plus C2 V2 plus CT VT. So you can actually express y in terms of this, I guess, linear combination. So you need some constant times V1 plus some constant times V2, dot, 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 plus some constant times VT to be equal to y. So for some C1, C2, up to C2, CT, which are real numbers. Okay? So in other words, if you go back to this picture over here, you have this, let's say you have these two vectors, and you were asking if let's say a vector is a linear combination of these vectors. So in order to be a linear combination of these vectors, the vector has to be in the plane which spans these two vectors. Okay, so just think of 3 space. So if you have like two vectors going like this and like this and like this, okay, all right, in 3 space, then the vectors in the linear combination of these two vectors, if and only if it's in the plane which is spanned by these two vectors. Okay, if it goes in like a different direction than the plane, then it's not in the span. It's not a linear combination. Does that make sense? Okay. All right. So maybe I just draw a few pictures here. All right. So let's see. Let's draw a few pictures. So let's say I just take a 3 space. Yuck. All right. So maybe we'll just erase that for a second. Let's try that. Let's try to do a better job here. All right. So so let's say I take 3 space here. Right. And let's say I take 2 vectors here. Let's make them blue this time. So suppose I take 2 vectors. I take this vector here, and I take that vector there, and let's call this V1 and V2. All right. So the vectors V1 and V2, if I look at linear combinations, I'm going to look at the plane spanned by these 2 vectors. Okay, so I'm going to look at this plane, which is spanned by these 2 vectors. Okay, and so everything in the plane will be a linear combination. So the plane, whoops, sorry about that. Okay, so here, the plane here represents all vectors that are linear combinations of V1 and V2. Okay? Good. Any questions on this?
So a linear combination is just a special case that the vectors are in the same plane. That's just basically it.
Sorry, I didn't quite understand the question. Can you repeat the question, please?
Sure. So linear combinations are just vectors in the same plane.
Yeah, so you look at the plane which is spanned by the vectors, kind of the plane that is generated by the vectors. And so the vectors which are linear combinations are the ones which lie in the plane.
Okay, thank you.
Okay. Okay, so now, all right, so let me just give you a little problem, and we'll work on this next time. Okay, so let's switch back here to the black. And so here's the problem. Let me give you the example here. Oops, come on. All right, so here's the example. So we'll start this problem now. So is 11 minus 5, 9, linear combination of 1, 0, 1 and the vector minus 2, 3, 0. Minus 3, 2. Question mark. All right, so we want to know whether 11 minus 5, 9 can be expressed as C1 times the first vector plus C2 times the second vector. All right, so let's set up this problem. So this is the same thing as saying whether 11 minus 5, 9 is equal to C1 times 1, 0, 1 plus C2 times minus 2, 3, minus 2. So can I find C1 and C2 for which this holds? Okay, so now let's write out what this means. Okay, so what this means is that I have 11 is equal to C1 minus 2C2 minus 5 is equal to, I'll just do it this way, 0 times C1 plus 3 times C2, and 9 is equal to C1 minus 2C2, C2. Okay, this is what this is saying. You guys know how to solve this or not? Yes or no? Okay, how do you solve? Gaussian elimination. Okay, so that's what we'll do next time. So the question about whether something is a linear combination of vectors reduces to a system of equations. All right, so this question reduces to a system of equations. Do we know how to solve systems of equations? Yes, right? So then we're going to apply the Gaussian elimination. Okay, so let me just say that one of the themes in this class will be that we have these questions involving like linear combinations and what's going to be called spanning, linear independence. And the point is that these questions are kind of maybe theoretical in nature, but then when it comes down to it, in order to solve them in specific cases, what we do is we apply the Gaussian elimination technique in order to do it. Okay, so part of the trick is to actually reduce things down so that you can actually use Gaussian elimination. So next time what we'll do is we'll finish off this problem, and then we'll do more when we actually recognize how to reduce things down. Okay, any questions about this? Was anyone able to get on and watch the videos at all? Anyone try? No? Okay, so everyone got the message about the homework. I think I've mentioned this before. Yes?
Yes.
Okay, very good. Okay, so we will see you on Friday.
Thank you.
Thanks.
Thank you.
Welcome.
Thank you.
See you. Okay. Welcome. Have a good day. All right. Okay, we'll see you.